All right, it's 1:25, so I think it's good to start now. Hi everyone. We're gonna go ahead and start with our workshop today on fundamentals of robot control. So just as a heads up, there's a Q&A in the blue jeans. So if you have any questions, then please use the Q&A to send them, and we're going to answer them during the presentation, either over text or we can talk about it verbally. And this presentation is going to be recorded, so I'm not sure how it'll be distributed to you guys, but it should be available for everyone to watch after the fact. Probably it'll go on YouTube or something. So today we're going to talk about a couple of different topics related to how you can make your FRC or FTC robot autonomous be a little bit performing better. And in particular, what we're going to talk about is some of the mathematical tools and algorithms that you can use in order to improve the performance of your robot in autonomous. And each of these algorithms, it builds upon the previous topic so that you can kind of take it step by step. And so in the middle, we're going to be showing some interactive code notebooks so that you can see a visualization of what these algorithms are doing. So just a bit about myself. My name is Varun Matabushi, and I'm a master's student in electrical and computer engineering at Georgia Tech. I graduated last year with my bachelor's in electrical engineering. And in the past, I've been a student of FRC. I've volunteered at FRC and FTC competitions, and I've mentored a team before. And my collaborator here is Jason. Jason, you can feel free to introduce yourself.
Sure. Hey guys, I am a robotics PhD student at Georgia Tech. I did my undergrad here in computer science. I did FTC as a high schooler. I was involved in robotics all throughout college. So feel free to shoot me any questions. I'll put my email at the end of the presentation, just in general, about anything related to college or robotics and what that looks like.
Yeah, Jason, if you want to put mine in as well, yeah, feel free to email either of us if you have any questions, electrical, computer engineering, or computer science related. So the FRC Autonomous Period is a particular challenge in robotics. No matter what happens in any type of game that there is, the challenge sort of boils down into starting in a particular location, using your drivetrain to move the robot to some point, and then at that point using a mechanism that's mounted on the robot in order to perform an action, and then from there you might have to move to another point and perform another action. And you can sort of see an example of this from Infinite Recharge. This is last year's game. The robot has to drive to a location, pick up a ball, drive to another location, shoot the ball, and it may do this any number of times. And seeing as the FRC Autonomous is only 15 seconds, you want to do these as fast as possible so you have more time.
Hey Varun, are you sharing screen right now?
Is that not visible?
No.
Oh, that's a problem.
Okay.
All right, how about now?
At least on my end.
All right. Let me check real quick. Sorry about that.
I have the live presentation up. It's just a little bit delayed.
Okay, cool. Well, we'll talk about that again. You know, there's pictures of me and Jason. Yeah, so we'll repeat this. As I mentioned before, in the FRC Autonomous Period, regardless of what game it is, the challenge really just boils down to moving the robot to a point, performing an action at that point, moving somewhere else, and performing another action. And you want to do this as fast as possible because you only have 15 seconds in the FRC game usually. And here's just a pretty straightforward example of that exact sequence. Go to a point, use the mechanism to pick up balls, shoot the balls, go somewhere else and pick up more. And this could be balls, this could be cubes from 2018, so on and so forth. And so in order to do this, your robot has to be capable to do those three things here, which is it needs to know where it is and know where it should be. So knowing where it is, the robot generally starts in a known location, and you know the layout of the field, so you have to figure out where you are in the field. And you can do that using a combination of sensors, traditionally encoders in IMU, which is an inertial measurement unit, and you can be supplemented with a camera. And then from where it is, it needs to decide where it should be. And you, as the programmer, you'll tell the robot beforehand what path it needs to take, and the robot needs to try to get itself to that path. And finally, it needs to be applying power to the motors. It needs to apply the correct amount of power in order to get the motors to go in the right speed in the right direction, ultimately causing the robot to end up where it wants to be. So we talked about 3 tasks earlier, each of them, and we're going to go into more detail about those tasks later on. Each of them is a tool that you can use on its own, but combined, you can actually have very highly performant autonomous. But work your way one step at a time. Maybe you won't even finish all of these in one season, but even going halfway through all of the ideas presented here would potentially help out your team. And for a lot of these control structures, there's examples that are even built into WPILib, which is the FRC programming library. So WPILib has some really great examples and really great tools to help you implement these on your robot code. And there's also many teams that have done this before, so you can always look at someone else's code and try to understand it and learn for your own. But one thing that looking at code doesn't really teach you is the mathematics behind it. And that's something that we wanted to highlight in this presentation. And so the math here that's required is pretty much something from the high school algebra and trigonometry level. So we're going to present it as simply as possible, but if you are having any difficulties, there's a lot of resources online. There's like websites like Purple Math, 3 Blue, 1 Brown, and also your high school's math teacher would probably love to help you out. That was a resource that I used when I was in high school learning these things for FTC. So the first thing that we're going to be talking about is odometry and localization. And what those words mean, odometry means you counting the rotations of the wheels in order to figure out where the robot is. And localization is just a general term for knowing exactly where the robot is in the field. So to start with, most robots in FRC are tank drive, or as we call it, differential drive. Differential drive meaning that the robot's motion is defined by the difference between the speed of the left side and the speed of the right side. And that's because they're independently driven. There's one motor on each side. And you can see that at any point in time, the robot is actually going to be traveling in an arc based on the difference between the left side and the right side. And here we see that the ICC is the instantaneous center of curvature. And that's actually the center of the arc that the robot is traveling along. So as you change the speeds of the wheels, you change the distance between the ICC and the center of the robot, which we're calling R. So your differential drive robot's going to be outfitted with some sensors. And the 2 essential sensors that you need in order to do your autonomous programming is you need encoders, which will count the rotations of the left and right wheels. And you need the IMU, which is inertial measurement unit. And in FRC, there's some pretty common ones that are plug and play that are the Talon SRX encoders or the AndyMark encoders that come built into the kit of parts chassis. and then the Andy Mark and Cross the Road Electronics both sell their own IMUs, which kind of hook into everything, like the NavX. And so with the encoders, you can measure the speed and the rotations of the wheels, and with the IMU, you can measure the rotations of the robot as a whole. So now we're going to talk about some of the key equations of a differential drive robot. So as I mentioned before, the robot, it actually travels along an arc at any point in time. If you give it a constant input to the left and right side, it'll travel in a shape like this. And here, there's a distance between the center of the robot and the center of the arc that it travels along. That's R, which is the instantaneous center of curvature. Oops. And as the robot travels along this path, it's going to trace out. The right side traces along this arc, and the left side traces along this arc. So you can see the left side's driven farther than the right side here. And the left and right side is spaced out by W, which is the width of the robot. So now you can measure L and R, which is the arc lengths here along this blue and red path. And you want to use those in order to calculate X and Y, which is the change in X and the change in Y position of the robot. And these equations here will actually tell you that this delta R and delta L symbols represent the encoder's measurement of these arc lengths. And then here L is just the width between the two. And from calculating here, you can, this is step one, plug this result in here and you get step two. Plug these two results here and here, and you have your X and Y. So these formulas, you can very easily type them into your code and they just work. And this gives you, at any point in time, you can tell the change in X and change in Y, given that your inputs were just a constant arc curvature. So now you might think that only works if the robot's only traveling in an arc. If you want to move in a complicated shape, what do you do? And the simple answer is you break that up into a bunch of arcs. But for every short period of time, you can follow these 4 steps. First step is measure the wheel displacements. And then you can calculate theta using either the IMU or those wheel displacements using the formulas. Calculate R, X, and Y. And then X and Y are just steps that you've made since the last known position of the robot. So you can keep track of your overall position by, at every point in time, adding your X and Y to your last known X and Ys. And from there, the robot can approximately keep track of where it is on the field. And so the more often you do this, the more accurate your location measurement is going to be. So the equations, they let you calculate robot displacement over short time steps. So as long as you can do this for a lot of different time steps, you can get a big picture idea and just kind of keep track of where the robot is. And the cool part is that those equations, you don't have to type them in yourself. There's a WPI-lib implementation for differential drive kinematics and differential drive odometry. So kinematics just implements the formulas, and then odometry lets you use those formulas. You can call them in a process in order to always keep track by measuring the encoder, measuring the IMU, combining all those measurements, and storing the last known position of the robot. And it's a similar process if you have a swerve drive or a mecanum drive, just kind of combine. You need more measurements for a swerve or mecanum because they can move in more directions, but the idea is still the same. So in reality, it's not so straightforward. The equations are what we call kinematic equations. They don't take into account things like forces, like friction, slip of the wheels on the ground, so on and so forth. And in fact, they assume that the wheels are perfectly in contact with the ground always. And we know that that may not be the case in all uses. So number one is your robot it can't brake too hard and it can't go too fast around corners, because both of those will cause the wheels to slip. And once the wheels are slipping, then your calculations, your measurements are all wrong. So when you're programming your autonomous, you have to make sure to keep a cap on your speed and keep a cap on your braking. And these equations are just an approximate solution. I mentioned that you break up your complicated motion into a series of arcs. They only work if your robot is moving in an arc for your short time scales. And so they approximate the shape, your complicated shape of your robot's path as arcs. And over time, that causes error to build up. So making sure that your error is kept reasonable within the 15 seconds of your autonomous period is important. So the next thing that we're going to cover is PID control. And if there's any one takeaway that you should get from this presentation, it should be about PID control, which is probably one of the most common and used algorithms for control in robotics, in industry, so on and so forth. So this is a diagram of a robotic system which uses a PID control. So the input is the goal, where you want the robot or mechanism or whatever it is to be. And the goal is subtracted from the measurement y, which comes from an encoder. And the difference between the goal, which is where you want to be, and the measurement, which is where you are, is created error. And you want the error actually to be 0. So the PID controller will take in the error and it'll decide what is the best voltage of the motor to input to make the error 0. So the PID controller outputs a voltage, which is sent to the motor. The motor then converts electric energy into force, which is applied to the mechanism. And then the sensor, which is in our case an encoder, measures the mechanism to show what the velocity is. And then this act of using a sensor to measure something about the mechanism and then using that measurement in order to inform your control is called closed loop feedback, because it's a closed loop here. And closed loop feedback lets your mechanism perform a lot better and more accurately, because you can directly control what you want it to do. So PID is essentially a formula of what voltage to give when you're given a particular error. So let's talk about if PID, it were just P, proportional control. And in proportional control, the error signal, you multiply it by a constant called Kp, and that's going to be your voltage that you send to the motor. So proportional control is very simple. You just multiply error by some number, and then that's the voltage. And the larger that this is, the more strength your controller will have, the more force it's going to apply in response to a particular error. And so when it's negative, there's going to be a negative power applied, positive when a positive power is applied. And this just causes a force in the opposite direction of the error. So proportional integral control is adding on an extra step to the proportional control. So proportional control on its own can get stuck. For example, if you're really close but not exactly at your goal, E is going to be very small, Kp times E will be very small, and then U will be very small. And the end result of this is that your robot just won't have enough strength to overcome any loads when the load is applied while you're very close to the goal. So we try to solve that with PI control, proportional integral control. And proportional integral control, it introduces a new variable called sigma. And sigma is just adding up all of the errors. So every time you calculate the error, you add it to your variable sigma, and it accumulates error over time. And finally, your controller is going to have u be equal to kp times e. This is the proportional term. And then ki times sigma, which is the integral term. And so even if e is very small and kp times e is very small, if your robot gets stuck, if e is constant but non-zero, over time sigma is going to grow larger and larger. It'll grow larger and larger until u becomes large enough to overcome that extra force that's causing the robot to get stuck. And one really good example of where you would want to use this is if there's friction between your robot or your mechanism and something else. If there's friction, then like static friction, then you need a little bit of extra force at some point in time in order to overcome it. And once again, there's another constant here called ki, which you can make large or small, and that will either increase or decrease the strength of this integrating effect. So with PID control, there's a set of 3 constants that you will have to tune until the robot performs in the way that you like. Then we'll talk about that a little bit later. So lastly, we're going to be talking about derivative control. And this makes up the third term, the D in PID. And this is used where if your robot is moving really fast or your mechanism is moving really fast, it'll have some momentum, which is going to make it harder to slow down. And so you want some effect that'll actually slow the robot down if it's going too fast. Or alternatively, if your robot is sitting still and you hit it and it causes it to jolt, you want to apply a fast correction in the opposite direction related to the fact that it's been jolted at a high speed. And that's derivative control. So here we have introduced another variable v, which is going to be the difference between the error and the previous error. And we can multiply this by another constant, kd. And this works just like proportional control and derivative control. So in various different cases, you may want to use P, PI, PD, or PID control. And you can sort of just test out different combinations of the 3 to see what works. So PID is really useful. You can put it in a lot of different situations, but there are some practical considerations that you need to obey. One is that the PID controller has to obey still the limits of the mechanism itself. For example, your PID controller might want to give 24 volts to your motor, but you only have a 12-volt battery, so you can only give 12 volts to the motor. So when you're using a PID controller, you have to make sure that your goals are well within the capabilities of the mechanism. For example, you can't, if your robot or your wheel can only spin at 200 RPM, your PID controller will struggle to maintain very accurate control at 200 or 199 RPM, because that's very close to the edge of what the motor is even capable of. So PID performs better if you give it some wiggle room above and below the goal. And the integral windup is another issue that you see with PID loops, which is where the integrator action becomes too strong and it causes the robot to want to go faster than it's capable of. And this is related to the control limits too, right? The integral may want the PID to output a higher value, but the PID is not capable of outputting more than 12 volts. So the solution is only updating that value of sigma when you're within a certain amount of error, or whether you're in a certain amount of whether you're within a certain amount of error or control output. And once again, like with the odometry, there's a WPI-lib built-in mechanism for this, which is the PID subsystem and PID controller classes. So the PID controller class directly implements those equations that I mentioned earlier, whereas the PID subsystem is how you can integrate that into your command-based software architecture. And this is really useful when you want to use a PID loop to, for example, rotate the robot or drive the robot a certain distance. However, if you want to use PID to control the speed of a wheel, for example, if you want to control the speed of your shooter wheel or the speed of your drivetrain, it's best to use the PID that's built into the Talon motor controllers. And the reason being that the PID loops, they run a lot faster on the motor controllers than they do on the RoboRio. And so the Talon SRX plus the Victor SPX motor controllers, you can combine those together and you'll have closed loop feedback directly within the motor controllers. You don't even have to write a single PID loop yourself. However, what you do need to do is tune those PID loops to make sure that the correct KP, KI, and KD constants have been selected. So once you've implemented a control, you'll see that there's 3 types of responses that your system can have. If you give it a command, it'll either rise up to meet that goal, it'll overshoot, and bounce back and forth. And this is what we call an underdamped system. If it's critically damped, it'll rise up to meet the goal and it'll reach the goal. Or when it's overdamped, it does that very slowly. So the exact amount of rise time, the correct rise time, results in a critically damped, or results from a critically damped system. So if you want your robot to meet the goal as fast as possible, your goal is actually to tune it so that it's critically damped, or as close to that as possible. So tuning is the biggest part of PID loops, and it's maybe the hardest part to get right. You might see, you have to kind of learn how to do this just by seeing, observing the robot and changing numbers. So you get the hang of it eventually. But there's some different cases that you might see. For example, if the robot gets stuck before it reaches the goal, it means you need to add integral control. If the robot's going too fast, you can decrease your proportional and integral gains. If it moves too slow, you can increase those gains. And if it oscillates back and forth, you want to increase the D gain. So this is in the case of it being underdamped. This is in the case of it being overdamped. And this is in the case of there's some unexpected loads on the system. So now I'm going to hand it over to Jason, who's going to give a quick demo of PID control.
Yes. So I just wrote up kind of a simple, it's Python-based kind of simulator plus PID, just to kind of give you guys the familiar with it. I'm going to talk a little bit about what you guys, or at least what I did when I was your age, working in FRC. You're going to see my terminal screen. But so the first thing we're going to do is we're going to essentially assume the world is perfect and have no noise. So what you're seeing here is the robot, the arrows where it's pointing. Here's like all of the history. Here's just where it's going. And then I have the wheel speeds down at the bottom. So this is the most perfect ideal world you could ever ask for when you're just doing open loop control is what we call it, which essentially means you're just setting like a velocity. if the world was perfect and there was no friction and all these things didn't exist, this is essentially what you'd get. You'd set some sort of power, and that would correspond to some sort of curve that would essentially decay out to the point where you're just hitting a constant velocity and you'll stay there. Now, this is really good, right? Essentially what we're trying to do is go from 1, 1 all the way out here and drive in a straight line. We're driving in a very straight line. This is great. But now let's look at what happens if I apply noise. We'll repop up here. And now we're seeing the exact same thing, but I have noise. This is much more what it realistically looks like when you actually go to run your robot. And as you can see, we are not driving in a straight line. And if you've ever done this before, you've applied power, and this is even better because I'm essentially assuming the wheels are equivalent and there's no difference between them. There's no slip. I'm just adding arbitrary noise. And you can see the velocities down here, how they don't converge to a single value. They kind of jump all over the place. This is mostly what you guys are trying to be seeing, the idealized case of what noise would look like. And you can see that when before we were almost exactly in a straight line, this is completely curving all over the place. So the next one is going to be, what if we did the same thing, but we did PID? So right now I have P. I have some gains, which we'll show you in a second. I will probably try to create a poll, but essentially what you can see here is I only have P activated, and P is a little bit too low. So I'm going to go through how to tune these loops, and I'm going to try to do some poll questions, and we'll see how that goes. So what we're going to do is we're looking at our code here. Don't worry so much about this on the screen. And we're going to look at our P constants. So right now we have a P of 1. Let me comment this stuff above that, actually.
Hey, can you zoom in a little bit so we can see the code a little bit better?
We shouldn't be looking at it too much. I don't think it's a problem. So I'm setting P to 2. And now we're going to rerun this simulation. So we're going to skip. We're going to skip the first one, and this is just going to be PID without noise. So you know how I saw before, we were sitting around 0.4. Now we're sitting around 0.7-ish. So we increase P to the point where it's good. And how you tune P really depends on your application. Like, at least for what I do, so I do aggressive autonomous driving for my research. And what you tend to see is, like, we want to over-tune it a little bit. That's probably what you're going to see me do here in a second. It obviously just depends on what you're trying to do. If you really want to reach that set point quickly, and it doesn't matter if you overshoot as much, then it's usually good to get your P a little high. So we increased our P, and I'm going to increase it again. I'm going to go really high, something like 20. So if we do a P of 20, what you'll probably see is, I don't even know if it'll handle it. Yeah. So what you're actually looking at is friction being a problem, but how I implemented physics here. So essentially what you're seeing is the controller is bouncing around. It's not converging to anything, it's just bouncing, and it's only doing this because there's no noise in the world, and I implemented friction correctly. So it does this, and this means your P is too high. Do you ever see something that looks like that on your velocity curves? Your P is way too high. So let's set something around like 8. So now if we look at a P of 8, you can kind of see the velocities down here. We're oscillating, but I think we reached our set point pretty quickly. And we're also not oscillating too bad, actually. So how you simply tune PID is you essentially want to increase your P until you're reaching your set point as fast as you probably want. So I'm going to do 6. So now this is more kind of what you tend to see as you have, it peaks up above it and then you kind of oscillate. So you want this kind of behavior when you do your PID. And then the next thing you want to do is you're going to want to increase your D. So what you want to do is increase your D to the point where it doesn't overshoot too much. So as you can see the difference between when I had no D and a D, before I had this kind of oscillating behavior up here. This one, it oscillated 2 or 3 times, and then it converged to a steady state value. This is kind of what you'd want to see from the optimal, from like a decent D. Like I'm just kind of arbitrarily playing with values here. there's always ways to tune your PID controller better. If you're spending an obscene amount of time tuning your PID controller, it's probably an issue somewhere else. Kind of how this tend to work is like, if you get decent values, you'll get like 90% of the performance, but the last 10% is like almost not worth tuning for half the time. So now,
sorry to interrupt, Jason. We got a question in the chat, or yes, I guess in a direct message to me. But are there programs to automatically tune your PID? So the answer is yes, to a certain extent. In order to tune the PID, you have to understand exactly how the system works. And if you want to do that automatically, it kind of means that a program has to move the robot, see how the robot reacts, and then change the PID loops gains on itself. And generally, that's actually not so safe to do because you don't want something automatically controlling the robot. There are various system identification tools that you can look into, which will kind of extract some characteristics of the robot. But to put it simply, it's usually easier to hand tune the PIDs than to automate it. I don't know if, Jason, you have a different answer.
No, I agree with that. I'm creating a poll. Cool. All right, there should be a poll. It'll probably take a hot second for you guys to get it. So I'm going to replay the simulation. So now, kind of what behavior we're seeing is the more technical term for it is steady state error. So essentially what that means is we're converging to a value that is not our set point. What we're trying to do is the green. We're trying to get the blue to go to the green. I left that out earlier. I apologize.
All right, the poll is online.
Awesome. So we essentially have 6 options of what we want to do. We can change P, we can change D, we can change I. And I do see 1 vote for increase I. How many people do we have?
We have 11.
Cool. So what I'd recommend is you guys do is vote. I'll give it 10 or 15 more seconds on what the optimal thing to do here is, and we'll see how it turns out. So I'm going to do, so now that we do have a higher D, we might be able to increase P a little bit and get a little bit better performance with respect to reaching our set point faster. So I'll show you guys what that looks like, although not exactly the answer I was looking for. So we'll do 8. So I said that's increasing P. So now that we have that D, what you'll see is we're settling closer to the actual value. But we can sit here and we can play with this P and play with the D forever to try to actually reach exactly to that point and finding the exact P that's going to correspond to it. Because remember, it's just a P multiplied by the error. So whatever this error is, I have to find a P that works here, but you can see that we overshoot even more than we did before. So really what you want to do is, which is 75%, which is increase I. Although increasing P is honestly not the worst thing you could do here. It's just the thing I was looking for, the way it's kind of set up is I. And that's just a question thing. So now we're going to increase I. So we're going to increase our I value, and we're going to see the difference. So this is even with that higher P, and see it's not a problem at all because you settle closer. So it's probably hard to tell on your guys' screen, but what you'd actually see is that the blue line is getting closer to the green line over time. As that accumulated error builds up, it is increasing the control value, but obviously not as much as we would want. So we're going to go for a higher I for 0.5. So that was getting rid of our steady state error, and now we'll probably do even better. So now you can actually see the 2 lines are converging. And again, with all things in control systems, it all just kind of depends on what you're looking for and what your goal is when you go to do these. So this could be like a really great tuning for my PID if I was doing something that was more safety critical. But if I was doing something more aggressive, probably for what you guys are doing, you'll probably want a little bit faster convergence. That should be fine. So now we'll have I. So I would say this is pretty good tuning of PID. And remember, right now we have no noise in the system, so this is what the optimal system would ever look like. We'll do noise in another second. So we do this, and we converge pretty quickly, and it looks pretty good. So let me show you what I looks like if I make I too large. This is the thing Varun was talking about earlier when your I is just way too large. And you can kind of see how we're having the same behavior as P, but it looks slightly different. It's not just directly oscillating. It kind of has some like lunges as it goes through. So this is how you know that your I is too large. So again, just to reiterate, as we go into the next section, how you tune PID is you set the I value, the P value, you set the until you reach your set point as quick as you would want. Then you increase your D until you don't oscillate as much as like oscillates with a reasonable amount, and then you increase your I to handle any steady state error that you might have. So now let's set P to 8. So now we're back to what, remember before when I had that trajectory when the robot kind of drove off on a line that was not straight? We're going to do the same thing, but now we're going to have PID. Oh, it's probably just the noise. We'll just set it to 2. Thought I pressed the wrong thing. So this is with our P2 low with noise, and you can see that we're no longer converging to a nice exact value. We're kind of oscillating around an area, and we're not handling it super well, but you can kind of see where it's converging to essentially the same. See that. So now we're going to increase P to something like 6. We're going to get probably a pretty good P here. I'll try to go a little bit faster. So now you're seeing more of the standard P behavior, but you're still the oscillation because you have the noise. And you can see how even with just P, compared to previously open loop controls, we're still driving in a much significantly more straight line, which is usually what you guys are looking for when you guys are doing control. So now I'll just use the same constants as before. So now we have this nice PID loop. So we have an I of 1 and a D of 1. And what you can see here is we never actually directly converge the value like we were seeing before. And that's just because the amount of noise I'm adding is kind of ridiculous, actually. So we're never going to converge to an actual value, and this is what you'll tend to see in hardware, just because things are always going to happen. And the whole point is that PID is compensating for it. But as you can see here, so this is our line, pretty straight. And now I will rerun the one with open loop control. So now what you're going to see is we run open loop control with noise. So this is us trying to just direct force application. This is what you guys are probably doing now with just setting the actual motor voltage. So you can see how we kind of curve off into a different direction. And remember, the noise between these two is exactly the same. Of course, it's going to be weird about the bottom now. But remember how from that PID control earlier that we were actually keeping within. So I think that's kind of a really quick primer on how to tune PID. You guys have any questions? We'll pause here for a little bit in order to make sure you guys can catch up to where I currently am. But hopefully that was instructive. Yeah.
Yeah, and feel free to post in the Q&A if you have any questions about anything that we've talked about so far. All right, if there's nothing, I'm going to continue on with the presentation. So the last topic that we're going to talk about for today is pure pursuit control. And this is a method of positioning the robot on the field and having it follow through a series of waypoints. So with the PID control, it's really good for doing point-to-point motion, which is just the simplest form of making your autonomous program. So let's say that your robot starts in this pose and it wants to end at this pose. First, you rotate until you're pointing towards the place you want to be. So you could make this rotation using a PID controller to rotate the robot. Then you want to drive in a straight line for a certain distance. Also something you can do with a PID control. So once the cross is reached here, then you want to rotate until you're in the final pose. So you rotate again using another PID loop. So here you make 3 separate motions: rotate, stop, drive, stop, rotate, stop. And so this might be covering the shortest amount of distance possible, but it is definitely not the quickest way of getting from point A to point B. So now here's an example of point-to-point motion in a pretty effective and straightforward autonomous from 2018. And I'm sure that you don't really need much to do this. Just your encoders, your IMU, and a PID controller is all you need in order to have an autonomous like that. On the other hand, if you want to smoothly move through a series of waypoints, you're going to want to look through an algorithm like pure pursuit. So in pure pursuit, when the robot is at some particular point, it will try to steer itself to point towards the look-ahead point. And the look-ahead point is just always a certain distance in front of the robot, and it moves along the line between 2 waypoints. So even the waypoints will look like this, and the robot will form a smooth path between them as it goes from one waypoint to the next. So in order to understand a pure pursuit control, it's helpful to understand a mathematical concept called vectors. And vectors might look complicated, but they're actually very straightforward. Every vector is just a pair of numbers, or at least every 2-dimensional vector is a pair of numbers. Let's say that you had 2 vectors u and v that are notated as having an x and a y, x1, y1, and x2, y2. Vectors, they have magnitude and they have direction. The magnitude of a vector is given by this formula here, the square root of the square of the first component and the second component, just like Pythagorean theorem. And they have a direction, which is defined as the angle between the vector and the x-axis, which here is just the tangent inverse of y over x. So you can multiply a vector by a scalar, which is just a regular number. Let's say that I multiplied this vector u by 2. It would be equivalent to taking 2 times x1 for the first and 2 times y1 for the second. And the end result is that you multiply the length of the vector by 2. So a unit vector is a vector with length 1. And a unit vector, we use it just to represent a direction. Since it has length 1, we can ignore the length and only look at the direction. And to convert an arbitrary vector into a unit vector, the unit vector is notated by this little hat over the letter. You take the vector, and then you divide it by its length, meaning that you divide x1 by the length of the vector, x2 by the length of or y2 by the length of the vector. And the way that you multiply 2 vectors together is called dot product. And the dot product takes two vectors and it returns a number. And it's just a thing that mathematicians have defined to be, if you have two vectors, you multiply the corresponding numbers of each vector together, and then you add them up. And this has the important property that the dot product of two vectors u and v, u dot v, is going to be equal to the product of the lengths times the angle between the two vectors. And we can use the dot product to do something called scalar projection, which is finding the length of one vector that's parallel to another. And you can kind of see it illustrated in this picture here. Or if you have a vector A and a vector B, the scalar projection of A onto B is that distance right there. Magnitude of A times the cosine of the angle between A and B. And here L is the scalar projected length, this here. It's given by A cosine theta, but can also be given as U dot V over the magnitude of V. And this tells you how much of the vector U is in the same direction as the vector V. And we're going to be using these concepts of scalar projection, unit vectors, finding the direction of a vector in order to do the pure pursuit control of the robot. So the first step of pure pursuit control is finding the look-ahead point. So remember that the look-ahead point is if the robot is off the path, it's going to try to get back onto the look-ahead point. It's going to try to rotate to face the look-ahead point and then make its way back onto the path. So we have to find it. So let's say that the path is a line segment from A to B. So we have two waypoints, A and B. And the robot is currently here at C. The first thing we want to do is find the scalar projection of the robot onto the path. Which means we want to find here this vector V and this vector U. We want to find the scalar projection of V onto this one. And U here actually can just be a unit vector. It just needs to be a vector that's pointing from A to B with length 1. And when you take the dot product of the unit vector with this vector, you get the scalar projection, which is the length of basically the position of the robot on the path. That points to this point here. So now that you know the length, the distance from A to D, we want to add the look-ahead distance, which is the distance between the robot and the look-ahead point here. And look-ahead distance is a value that you can specify, just like in PID where you have to tune the PID loop. For pure pursuit control, you want to tune the look-ahead distance. And a larger look-ahead distance means that the robot will turn more gradually to make its way back onto the path, whereas a smaller look-ahead distance is going to cause the robot to turn sharply and try very hard to stay on the path. So once you've found the look-ahead distance, now you have a length from A all the way to E. And you can multiply this by the unit vector that's pointing in the direction from A to B. And the result is a vector that goes from A and specifies the coordinates of E. So now that we've found the look-ahead point, now we need to see how do we steer the robot to go in that direction. And we do this by finding a vector that points from the robot to the look-ahead point. And now this is going to be the direction that we want to be facing. And using odometry or using the IMU or whatever, you'll know what direction the robot is facing. So the first thing we need to calculate is we need to calculate the angle error between those. Calculate the error between the robot's angle and the look-ahead distance goal direction. And we can multiply that angle error by some correction factor. This is just a proportional constant, so it's just like P control of the PID. And finally, we take that correction factor and we add it to one side of the drivetrain's power and remove it, subtract it from the other side of the drivetrain. That way, one side has negative power, the other side has positive power. And the end result is that the robot steers in that direction. So lastly, we can talk about how do we follow a path. First, you want to apply a constant power to the left and right side motors. So maybe you start by giving it a base power of 50%. Then you calculate the look-ahead point, compute the steering adjustment, and then add that to one side of the drivetrain. So let's say your steering adjustment finally is 15%. By the end of step 3, you would have on the right-hand side, you would add 15% to the right and subtract 15% from the left. So you'd be at 35-65 for left and right. And the end result is that the robot will curve to the left because the left side is getting less power than the right side. And lastly, you have to check if you've crossed the current waypoint. And if the look-ahead point crosses the waypoint, you have two options. You can either start steering towards the next waypoint, or you can stop the robot because you're close to the end point. It's important to know that for pure pursuit, you don't actually stabilize the robot at the goal point. You have to have some code in there to check, oh, have I reached the end of the path? And if you've reached the end, then stop the motors. But yeah, now we're going to go into a notebook demo. So if Jason, you want to take it away?
Yes. So if any of you guys have been looking at what's been going on and being like, wow, this seems complicated, I could easily mess that up. Fun for you. So did I this morning, actually, as I was implementing this algorithm. I actually don't have a fully functional implementation to show you. But I found a nice graphic online. We'll talk about it, and then I'll show you what I do have. We can all fit my lack of knowledge. So this is kind of what you're seeing with Pure Pursuit. My screen. Essentially what they're doing here is they're creating a path full of waypoints. This is kind of what you tend to do for, at least what we tend to do for FTC. But hopefully this works for FRC. I don't know. We use it in my research a lot. So now you're essentially doing Pure Pursuit. And what you can see here is this is the target point that it's trying to reach. Here's the actual current position of the robot. And it's just trying to point itself in the angle of the essentially the target point. So it's just trying to drive directly to that target point, and you can see as at the end, the target distance, following distance, essentially straight. So this hopefully makes more sense of like what Pure Pursuit is trying to do. You're just trying to drive to that point. And I will now show you my somewhat functional version. So you can see here, we have our motors like we had before. We have our drive right here, and we have this point. Essentially, we're trying to find this point, and you'll see it start to move down the path a little bit here. And we're just trying to point ourselves at that point and then drive with some nominal velocity. This is our full state trajectory plus essentially what our waypoints are that we're trying to follow. So a lot of times, especially when you're working with angles in robotics, they're really easy to get wrong, which is what you're going to see in a couple seconds here, is that essentially, I'm not properly handling. So when you do angles, if you guys haven't really covered it before, essentially you have between negative pi and pi is what you usually see. Yeah, so now it's doing wrong. Essentially, how I'm calculating where the point should be, somewhere I'm flipping. I'm not properly handling the fact that your essentially angles are not continuous values. They're between negative pi and pi at any given point. So when you switch from pi to negative pi or negative pi to pi, I'm not properly handling that, and that's why it essentially goes backwards, and then it just kind of doesn't know what to do after that. But either way, there's a lot of implementations of Pure Pursuit online that are not too bad, and if you spend the proper time on it and really write down the trig instead of just trying to guess at it like I did, you'll be totally fine with this algorithm. And there's a lot of good applications for it. So you might be like, oh, so I know PID and I know pure pursuit. What can I really do with this? So this is some people that I've worked with before out in Berkeley. Oh, sorry, this is Stanford. My bad, I haven't worked with these people. But they're essentially what they have right here is a fully autonomous DeLorean. And essentially what they're trying to do is drift the car as fast as they can. So this is essentially just using pure pursuit and PID. They're using a little bit of adaptation online as it drives. So essentially it changes the PID constants as it drives. So it's a little bit more advanced, but like fundamentally not that complicated. You guys could totally learn how to do this. It's mostly just the application of the thing that's the complicated part. And someone letting you do this to their car. So if you're ever like, wow, I'm not learning practical things, right here. All of these really basic algorithms can get combined into something really complicated and really interesting. Do you guys have any questions on pure pursuit? Let us know. I don't have much else to talk about unless there are questions.
Well, yeah. Our contact info is up here. Jason has a little note. Feel free to ask me any questions about robotics in college, etc. Yeah. I'd say the same goes for me. Feel free to ask either of us anything. Those are our emails. And I mean, I think I have done a little bit of FRC stuff compared to Jason, so I can answer some FRC questions if you would like. But yeah, thank you guys so much for coming. I know that this FRC season is going to be a little bit weird because of the online aspect, but as they showed in the video, I think there's an autonomous skills challenge. So I hope that you guys get the chance to get your hands on the robot, write some PID controllers, and tune them, and hopefully have a really good autonomous skills run. But yeah, have you guys used any other algorithms in FRC Autonomous? Usually a lot of these things build off of each other, and there's a lot of I would say there's a lot of body of work made by the really highly performant teams in FRC Autonomous. I'm sure many of you guys have heard of Team 254 or Team 11678 that are from California and have really high quality autonomous programs. And that usually comes from building your way up. You have really good motion control or really good wheel control if you can get the wheels to spin exactly the way you want using PID control or whatever. And the next step on top of that is they have developed a really good trajectories of how to get around the field, and then they follow those trajectories really accurately. The algorithms that we mentioned here kind of make up the core of how to do that. You can add more things like, oh, we want our trajectories to be optimal, that it's the absolute fastest trajectory. Maybe you want the trajectories to include some speed up at the beginning, so you can gently speed up the robot and gently slow down the robot at the end. You can add that on. That's called motion profiling. So there's more stuff that you can keep adding on, but this is kind of the base right here.
You guys have focus on the FRC questions. So if you have less FRC specific questions, also feel free to ask those now. Something else. I don't see any other questions. So.
I mean, I guess other algorithms too, besides control, is the real thing that we didn't really cover at all that was part of this, but is really important in FRC is vision tracking and camera tracking, which is something that used to be a lot harder back in the day. But these days you can kind of just buy that. The Limelight camera, for I think $300, kind of has all the built-in tools to see any of the retroreflective targets from the FRC game. So a lot of stuff that you could do in camera image processing, but really the Limelight kind of does that on its own.